Hello, and welcome to a new lecture on Cantera. Today, we will be learning about how to calculate standard enthalpies of reaction using Cantera. So the standard enthalpy of reaction is the enthalpy change when a reaction occurs under standard conditions, which is to say 298.15 Kelvin temperature and 1 bar of pressure. And the way we calculate the enthalpy of reaction is that we first take in the enthalpy of products that are formed, and then we take the enthalpy of reactants and then we subtract them, and the resultant is the enthalpy of reaction. If we get a negative quantity, that means it's an exothermic reaction, so the heat is liberated. If we get a positive quantity, it means it's an endothermic reaction, so the heat is absorbed. So we will see this with an example. The example we will take is oxidation of ethane. So 1 mole of C2H6 plus 3.5 moles of oxygen gives 2 moles of CO2 plus 3 moles of H2O. That is a balance reaction. And if you calculate the heat of reaction by hand, you will find it to be about minus 341 or negative of 341.16 kilocalories. Which means it is an exothermic reaction. So we'll try to do this with Cantera as well and see how close we get. And the same concept will be applied or will be applicable to any reaction as such. One thing to keep in mind is that enthalpy of reaction is an extensive quantity, and so it depends on how much of quantity of reactants and products are there. So we will have to take into account the moles that have reacted. So 1 mole of C2H6 and 3.5 moles of oxygen, all of this will figure into our calculation. So let's quickly start with Cantera. I'll bring it up. And I think you already know by now how to start Cantera or start Spider on Anaconda. So you go to the start menu, you look for Anaconda, and then underneath you will find the Anaconda prompt. Go to Anaconda prompt or click on Anaconda prompt, and then say Conda activate the name of the environment that you've set. And then after that, once the environment changes, which will be shown on the screen as well, then you just write Spider, enter, and Spider IDE comes up. So let's start writing the program on calculation of standard enthalpy of reaction for C2H6. Let's just for reference write this reaction of ethane. So I will start this with a pound key to display that it is a comment. C2H6 plus 3.5 moles of O2 gives 2 CO2 plus 3 H2O. I believe this was the reaction. 2 CO2, 3. Yep. Okay. All right. Now, what we will do is first we will set the reactants and find the enthalpy of reactants. So let's first import Cantera. Import Cantera as CT. Oh, here I've used a capital I, it should be small. Import Cantera as CT. And then I will initiate an object of the solutions class. So gas equals CT dot solution. Let's enter the GRI mechanism, because GRI has all of these species. It has C2H6, oxygen, CO2, H2O, all of that is there in GRI mechanism. So we'll just say GRI So T dot IAML. All right, now let's go ahead and set the gas composition or the gas state of the gas to the reactants. So we will say gas.tpx equals standard conditions, right? So 298.15, comma, 1 bar, comma, this is C2H6, 1 mole of that, and O2, 3.5 moles. Okay, so this is the, let me write comments as well. All right. Now, let's say calculating the enthalpy of reactants. So if you remember, in the previous lecture, we've discussed the function enthalpy mole. And so that gives the joules per kilomole of the mixture, the enthalpy in joules per kilomole of the mixture. And so we will just go ahead and use that same function. We will say H react, so enthalpy of reactants is equal to gas dot enthalpy mole. All right. Now, this is where we have to use some brains and some tricks. So this here is enthalpy in joules per kilomole. However, you have to factor in the moles of the reactants as well. So let's first convert this into joules per mole. And so we will just divide this by 1000. And now, if you remember, when you supply a mixture to Cantera, the mixture is automatically normalized. So Cantera says, okay, I'll have 1 mole of mixture, and then it just divides all the components of the mixture into the same ratio that you specified. So 1:4, so total number of moles, if you see here, is 4.5, 1 plus 3.5. So Cantera says, I will put C2H6 as 1 divided by 4.5, so it is normalizing, and O2 will be 3.5 divided by 4.5. So, but here in reality, we are actually reacting total of 4 moles, right? We are not normalizing. And so we will go ahead and multiply this by 4.5, which is the total number of moles that are present. All right, so this will be the enthalpy of reactants. Now, let's set up the product mixture. Product mixture. Here, I mean, since the temperature and pressure stay the same because it's all standard conditions, we'll just write gas dot TPX equals none because the temperature stays the same, none because the pressure stays the same, but the composition will change. Now, the reactant composition is this: 2 moles of CO2 plus 3 moles of H2O. So I will write CO2 to H2O 3, right? Okay, and just hit enter. So this is the product composition set. Now, similarly, we will do the same thing here as well. So H of product equals gas dot enthalpy mole. Again, we will divide this by 1000 to convert it into a number of moles from kilomoles, and then multiply it by the total number of moles present, which is 5 in this case. So we'll say 5, right? And so this is the enthalpy of products. Now, if we have to write Now, so this is product and reactant enthalpy. Now we will just subtract them and find the enthalpy of reaction. So the enthalpy of reaction will be, let's say, Rxn, looks right, equals H of product minus H of reactant. All right, so this is the heat of reaction. However, all of this is in joules. On the slides, we saw it was in kilocalories. So to convert joules into kilocalories, we have to multiply it by 0.00024 or 23. Yeah, 0.00024, I think. Then we'll just write H reaction kilocalorie equals H reaction into 24. All right. Okay. So now let's just print this number. H reaction kilocalorie. Let's see what it does. First, we will have to save the script. Let's save it in documents. Enthalpy reaction. Save. Okay, let's keep our fingers crossed and actually I need to add some comments here as well, but let's quickly go and run the code and we will do that too. All right, so 3 minus 342.87. Let's see, what did we have here? Minus 341.16, so pretty close. I mean, within very, very small percentage. So that is how it's done. I'll add some comments as well quickly. So this here is the calculating the enthalpy of. I'll just copy the comment from here and I'll paste it here. Calculating the enthalpy of products. And this here is calculating enthalpy of reaction. And here this is converting joules to kilocalories. All right. And maybe we should write something here as well. That's fine. So, okay, so that was it. This is how you calculate the enthalpy of reaction for any reaction. I mean, just write the balanced equation, and then according to the balanced equation, you have to just set the right coefficients. And so this is the easiest way. And again, there could be several other ways as well. And as you progress, as you increase your skills in Cantera, you may find some other ways, some other functions that may do it differently, may do it easily, easier than what I've showed you here. This happened to be like a very sort of a fundamental type of approach, and that is why I took this one. So I do encourage you to look for other methods as well, and that'll be all. Thank you.